Now, so now we're ready to move on to a major subtopic called optics. I say it's subtopic because, like I told you at the beginning of this unit, anything we talk about in waves applies to all waves. Now, though, we're going to turn our attention specifically to light waves and how we manipulate them using mirrors and lenses. And that is the subtopic that we call optics. Before we get into that, though, there's something important we need to discuss, and that is, if I were to bounce this ball to Haley, I'll hit Morgan, yes. I'll hit Morgan. I'm going to bounce it like that, right? No. Good. Now, what's going to be different about how I throw it to get it to Brandon? More art. You mean like little distance? What was different? The what? Yeah, the angle I aimed it at, right? When I wanted it to go to Haley, I did a steep angle, right? So that it came up like that. When I wanted to throw it to Brandon, I did a more shallow angle. Yeah, there we go. Where's the tiny wings? Now we're going to do the tiny wings. Yeah. And why is that? Because it's going to reflect at whatever angle I throw it. This is what's called the law of reflection. Not only does it work for golf balls and tennis balls, basketballs, but it works for all waves, all times. That's what's called a law. Simply put, the law of reflection says that the incident angle is equal to the reflected angle. Incident angle? Yes, sir. Now, just for those of you going out next year, this is measured from the normal. So, for example, incident and reflected. So, for example, here's a normal, right? Normal means perpendicular to. So, if I have an angle, I have a ray coming in like this at this incident angle, it's going to bounce out, right, where that reflected angle is equal to that reflected angle. Yes? Good question. We're not talking about, well, first of all, it depends on what kind of wave as to whether or not it loses energy. But even assuming it does lose energy, it's a type of wave that loses energy, we're not talking about the magnitude of its wave speed, for example. We're only talking about its direction. Okay. So that's like that. All right. Now, the first thing we're going to talk about in optics, then, is the mirror. What's a mirror? Piece of glass. Piece of glass? Mirror. Silver or nickel or some kind of metal into a piece of glass. And what's the purpose of the piece of glass? To reflect light. Or to reflect a lens. Give a little light to a crack. Light. Huh? I just want to keep it clean. Keep it clean or protect it, right? Because you don't want your silver getting scratched up, right? And so that's what the glass is there for. Yeah, scratches. Now, what is it then about that silver that makes it a mirror? It reflects all the light. Do you agree? No. No. What do you think? I think so. Point to back. I think this. It's always in contact everything. I feel like you're making
You're doing a double curveball. You should cop out.
How much of the light is this reflecting?
No.
All of it. Why do you say all of it? Because it's white, and white is a combination of all the colors, and so if it's reflecting all white, then it's reflecting all the colors. So,
It reflects all the light, but in different places. It reflects the light. It doesn't reflect like, it's not all the colors mixed together.
No, it reflects off the glass, right?
The light reflecting on the view doesn't reflect off this.
You don't like the object, you see the light.
in a mirror?
On the paper.
Oh, right, so this isn't a mirror, right?
But that does reflect the light.
But it does reflect all the light, so what's the difference?
It's like,
Yeah, it doesn't relax, so you can't.
because it's not.
So, what's special about the silver?
Because it's metallic.
It doesn't absorb the
It
light.
makes you see yourself
It
in the
reflects.
mirror.
Why?
Because the light is
Because God made
Because
it
it's
that way.
Because of what they said.
Because the
They
brain.
cut that physics.
What is true about this, even though it's really dirty, that is not true?
Yeah.
Put some glass on it.
Oh, okay, so yeah, just put a layer of glass on this and it's fine, right?
Yeah. No, silver's not.
Why the silver?
It's shiny.
Why is it shiny? Why are other things shiny? Okay, polish. Why are polished shoes shiny? They have a coating that makes them shiny. Right.
Is that where the cord on the board came from? I was thinking about
Yes.
my shiny shoes.
Because it's smooth.
Smooth. Okay. Aw. I'm sorry. Let me illustrate my point here.
So paper is completely smooth and
The paper's not glass, it's smooth.
Right, paper is not smooth.
what if you got a really smooth white thing?
We're getting there. Getting there. Now, so,
So what if you're still...
here comes an incoming ray.
Oh, it bounces off the board instead of getting lost in the
Okay. What did we say about the law of reflection? It's going to bounce out at the same angle relative to a normal. So it looks like that. Now if I draw another, in this case blue ray coming in, how's it going to reflect? And then let's do a green. What do you notice about the rays? They're parallel coming in and perpendicular going out. Or parallel going out. Okay? Now, let's draw those same rays hitting our sheet of paper.
I don't think that's the sheet of paper. I think it's
Look, what's the direction of the normal now? It's perpendicular to the surface, so it's like that. Does the ray follow the law of reflection?
Yes, it's a law.
It's a law, exactly.
Always follow the law.
That's right. That's why it's called a law. No known exceptions. Now, I'm going to draw the blue wave that coming in was parallel to the red wave.
Well, what's the solid thing? Is that the mirror and the crumbly thing is the paper?
Yes, this is a mirror and this is paper.
What the heck? Like the flat one is the mirror? What?
Whoa.
Okay. Your lines are really straight.
Thank you.
They really are.
And then green. Okay, that one wasn't very good, but you get the idea. Now look. When they bounce off the paper, they come in parallel. Do they leave parallel? No, because the surface isn't smooth. They still follow the law of reflection, but because of the bumpy surface, the normal's constantly changing, and so parallel lines coming in leave not parallel. This surface over here will produce what we call an image.
So do they leave perpendicular?
This over here is what we call diffuse reflection. It diffuses the rays, doesn't allow them to stay parallel.
So if they're not parallel, you can't.
And the way I see an image, right, is a light ray from this part of the hammer hits this part of my eye. A light ray from here hits this part of my eye, boom. And since those light rays come in and hit next to each other on my eye, my brain can assemble an image of this hammer. If those light rays don't come in next to each other, they get all jumbled up, they don't hit my eye in the right orientation, I don't see an image of the hammer.
Is that whenever you have like contact sunglasses?
You know what?
In a spoon, you can like see a reflection.
Okay? What's true of the spoon?
It's smooth, but it's all bent and stuff.
Yeah, we're going to get to shape, what's called so-called true mirrors later. Okay? But the fact that they're smooth allows them to produce an image, even if the image is different than your face.
Wait, is paper not smooth?
Right.
No, paper is not.
So, hold on, let me finish these thoughts and I'll pick up your questions if I don't get them. So, does that mean that anything smooth can produce an image?
Yeah.
No. Yeah. If it's truly smooth. So what are some examples of some things that produce images because they're really smooth? Water. Right? If you look into look at the lake, you see images, right? Reflections of whatever on the other side. Or if you look over, you can see a reflection of yourself. Because that surface of the water is very smooth. So the light can reflect and produce an image. It's also why driving at night in rain is very dangerous. It's not that the lights from a car coming towards you reflect off of the ground, right? If it's not raining, and let's say you're a pedestrian, so you don't have any lights of your own. An oncoming car. Shut up. An oncoming car. Do the headlights from the oncoming car reflect off of the ground when it's not raining?
No. Yes.
Yes.
Yes. How do I know that?
Because you can see
Because you can see the ground. How do you see the ground? The light's reflecting off. So again, it's not that the light's reflecting off the ground when it's wet that makes it hard to see. It's because when that light reflects off the ground, how does it reflect in the rain? Parallel. So not only do you see light from a headlight, you see the whole headlight. You see an image of a headlight, which is a lot brighter than just the diffuse reflection that normally happens on the ground. And so that's what makes it so hard to drive. You get all those shiny reflective surfaces because everything gets wet and therefore smooth and therefore produces images. Another example.
Like a window.
Window. Or an old TV, right, with a glass tube. Glares. Right? Glares are what? Images. They're reflected images.
From like the sun?
It depends, yeah. I mean, like a window, like the sunlight coming in from the window, if the TV's over there, you see a glare on the TV, or even on the mat. See the glare on the mat? Right? It's a smooth surface, therefore it produces an image of the window. That's what we call a glare. Now, Hold on. One more. We already mentioned how paper is very rough, generally. And so it doesn't produce images normally. If I'm let's say I'm laying down in bed, can I hold a book like this and read the book like this angle?
No.
Yeah, I mean, if I have good, I'm a phone awake, right? If I have pretty good vision. If I exchange that book for a magazine, can I do it? No, because the pages of the magazine are shiny, they're glossy, and so they produce images, and so I get glares. And so I have to look pretty much straight on. I can't have any outside light that can produce an image on the page that keeps me awake. Not like that. I get like this. Like the page is slightly angled.
Oh, okay.
Yes.
On the newer computers, if you can bend the screen so that it's more clear, what's the effect of when you make that angle really, or it's really deep, and it's like dark across the screen, you have to pull it up so you can see it. What's the effect in the glass? Like, how do you do that?
It's like little louvers, so that the light only comes out parallel, so that it doesn't go out in all directions, so that it's like a privacy screen or whatever, so the person next to you can't see what you're doing. It's like on street stoplights a lot of times, they'll have those louvers to where it shines straight out, so somebody in the turn lane doesn't think they have a green light when they really have a red light by getting the two confused. Same concept. Yes, sir.
Have you ever been on like the charter bus where you can you're like leaning against the window and you can see out like that the other side, like the other side of the street that's coming this way?
Oh, yeah. Exactly. The window in the bus is a smooth surface that then produces images of the other side. Exactly. Question.
So with the camera example, like it directs your eye, is that what you need, like, you need glasses
We'll get the glasses when we do lenses. That's up. All right, we'll see you.